All right, ladies and gentlemen, class recording has begun. So, we have talked a lot during the year about making graphs. Why do we make graphs? What's the advantage of making graphs? Represent data in a different way. To show changes, right? What? It's been in the drawer for like a month. So. Rachel. See relationships and see patterns, all right? Those are reasons why we make graphs. And so that's what that's what you guys did the past couple of days with your lab, and that's what we'll talk a lot about today. So we're going to graph motion. Now, when we talked about motion, we said that there are 4 things that we would like to know about an object. Go ahead. There are 4 things that we would like to know about an object in order to describe its motion. 4 questions that we want answered. So, what's the first question that we want answered in describing the motion of an object? Where is it, right? Or what's its position, right? So the answer to that question is position, right? Okay. When we describe the position of something, we need to set the groundwork first, right? What do we need to do before we describe the position of something? Reference point, and then direction system, right? So we got to figure out the reference point, where are we measuring from, and then which direction are we going from there, okay? Second question that we want answered. What do we want to know next? So where is the object? What's next? What is it doing right now, right? And so we learned the other day that we call the answer to that question. What's the answer to that question? What is it doing right now? It could be nothing. Could be something. What do we call the name? What do we call the term that describes what it's doing right now? Displacement is how far did it go? Uh-oh. Might have to open up the notes and look at yesterday's outline. What? Nah. Speed is not quite descriptive enough, Jafar.
Am I close?
Average velocity or velocity. All right? So, position tells us where. Velocity tells us what. And then time tells us when. Right? So, where, what, when. These graphs of motion will answer those questions for us. Okay? Why is the next chapter. Okay? We get into forces in the next chapter. Forces are why. Okay? So we'll get into that in the next chapter. Okay? Don't worry, we'll get there. Alright, good? Okay. Here is a picture of 2 swimmers and a graph of their motion. And directly next to the picture of those 2 swimmers and a graph of their motion, there are 4 questions that I would like you to answer about their motion based on that graph. So, here's the 4 questions, right? There's the graph. You have the graph there too as well. Let's take about 30 seconds and let's answer these 4 questions based on that graph. If you want a bigger version of the graph, I'll leave it up here so we can answer the questions. You can see it a little bit better. So, 30 seconds. Talk to the person next to you. Answer those 4 questions about the graph of those 2 swimmers. Go.
40 meters. 40 meters from Facebook.
No. Yeah.
What do we? If it's a graph, right? You're on the right track.
It would just be 40.
40 meters.
Plus, wouldn't it just be 40 meters?
One is something else. Write them down. Write them down on the sheet. We'll go through it together.
It's in 20 seconds. 20 meters. meters per second.
The other is probably should be. That's pretty easy, right? So you have a copy of it there too. You? Yeah. Oh, there you go. It's a little smaller there than it is up on you.
No, I get it. Oh.
I'll tell you in 10 minutes. All right, are we ready? Okay. Question number 1. We said position describes where this object is, right? How many of us wrote this? 40 meters. How many of us wrote that? You tell me, am I kidding? All right. So, we said that position, in order to describe the position of something, we have to define a reference point, we have to define a directional system. Okay? In the case of this swim race, what's probably the reference point? Where is that in the relation to the swim race? The starting line, right? Blocks of the swim race, okay? And then probably it makes the most sense to call the direction that you're swimming in the positive direction, and that means that anything behind you would be the negative direction, right? So here, assuming that this person jumped into the water and started swimming in that direction, right, and didn't turn around and walk, on the pool deck, we could say positive 40 meters, all right? So, number 2. How far ahead of swimmer number 2 is swimmer number 1? Because this is just asking us how far, right? It's perfectly fine there just to answer 20 meters. Okay? You just read the graph on? All right. Next, displacement, right? We said displacement tells us how far we are from where we started. Right? Now, in this case, it's asking you displacement not for the race, but for a certain period of time. Right? So, from 10 seconds to 40 seconds. So swimmer number 1 was right here at 10 seconds, and right here at 40 seconds. So how far away are they from where they started, at least during that interval? 60 meters, right? But displacement being a vector quantity means, what else do I have to tell you? Which way did I go 60 meters? Forward, right, or in the positive direction. Okay? Ronnie, does that help? How far are we from where we started? Right? That's what displacement basically is. Okay? Actually, I should say, how far and which way are we from where we started? Okay? All right, last question. Which swimmer is faster? Swimmer number 1 is faster. How can you tell that from this graph? Well, okay. 2 things we can go about it 2 ways, right? Go ahead.
Has a greater velocity?
How can you tell that it has a greater velocity?
It's steeper.
Okay, so yesterday, while you guys are making your graphs, we learned what property of that graph tells you about the velocity. The slope. So swimmer number 1 has a greater slope, right? But if we just talk about fast, right? Fast is distance over time. How long do each of those swimmers swim for? How much time do they each swim for? 50 seconds. But what do you see about swimmer number 1's distance during that 50 seconds? She went 100 meters, whereas swimmer number 2 only went, well, they have those little swimming caps on, so I'm going to assume. Not that they always, but I would assume that they are.
Does it matter?
And they also, yeah, they have a little strap on the swimming suit there. So.
50 meters for swimmer 2?
Yeah, so swimmer number 1 goes a lot farther in the same amount of time, so she has to be going faster. Okay? Good there? All right. There's one thing I would change about this graph if I was to make it on my own. I would change the label on the y-axis from distance to position. Okay? And that makes this a position versus time graph. So, what does a position versus time graph tell us, at least in a duh kind of way? Position and time, right? So it answers two questions for us. What two questions does it answer? Where and when, right? So position versus time graph tells us the location of an object relative to a reference point over a specified period of time. So position versus time graphs answer two questions for us, right? They tell us where, and they tell us when. Where and when. That's what a position versus time graph tells us. That's in an obvious sort of sense. But over the past couple days, and especially yesterday in the lab, we also learned that a position versus time graph can tell us a third thing. It can also tell us velocity. Right? So, if we look at slope, slope is a concept that you get introduced to mathematically way back in pre-algebra, right? Or whatever. So, slope on any graph is a relationship between two things, right? What is it a relationship between? How do we define the slope of something? Distance over time is too specific. When we're talking about slope in general, what is it? Rise over run, right? That's the slope of any graph. Now, when you get a little bit more sophisticated mathematically, we define it this way. Delta y over delta x, right? But you guys know that notation, right? The delta means what? Change. So if it's delta y, that's change on which axis? The y-axis. And if it's delta x, it's change on the x-axis, right? Rise over run. Okay? Now, this is true of any graph. But if we now take it and look at our graph specifically. So remember we said, let's get rid of distance here, and let's call this position. Okay? If we look now at our definition of slope, delta y is now delta what? If we apply these concepts of slope to our position versus time graph, delta y now becomes what? Delta position, right? Change in position. Does that make sense? Okay.
Yes.
Because position is on the y-axis of this graph, right? So delta y, if we apply it to this graph, is now change in position. Change in position is the definition of something that we talked about 4 days ago. Change in position is the definition of what? Displacement. Right? So, delta y is change in position, but change in position is how we define displacement. What's on the x-axis of this graph? Time. So now delta x becomes delta time, or delta t. And that means if we take these ideas of slope, rise over run, and apply them to this graph specifically, we end up with displacement over time. And displacement over time is how we define what? Velocity, right? So the slope on a position versus time graph tells us the velocity. Okay? Ronnie, go ahead.
When you're talking about displacement, you're asking a question, do you always give us a reference point and then a ending?
We have to do that, okay, for displacement. I would have to tell you where it starts and where it finishes, okay? Now, sometimes it might make more sense for you to figure out the reference point, okay? Because you can basically call anything you want the reference point as long as you keep it consistent throughout the entire situation that you're measuring stuff, okay? There's going to be an example later on that I'm going to use that I will show you what I mean with that, okay? So, but if I'm going to ask you to find displacement, I got to tell you where it started and where it finished, okay? So that could mean in something like this, I could ask you for the displacement of the whole race, right? And that means this would be the starting point and this would be the ending point. But like I did on the previous screen, I could ask you, I just want to know the displacement from there to there, right? But I'm still giving you a starting point and ending point. I got to do that if I want you to calculate displacement. Okay? Does that make sense? All right. So, slope on a position time graph tells us velocity. Also, if we take a look at units, right? What unit is on the y-axis? Meters. What unit's on the x-axis? Seconds. Meters over seconds, that's the unit for what? Velocity, right? So even from a unit standpoint, we're pretty good. Okay? Does that make sense? No, go ahead.
Would you have to change it if it was kilometers?
That would make it a different unit, but technically, Noor, any distance over time measures velocity. It just might not be an SI unit. Does that make sense? Like kilometers per hour still measures velocity. It's just not an SI unit. Or miles per hour. It's still distance per time, but it's just not SI units. Okay? They would still tell you the same thing, just maybe not in meters per second. Okay? All right. Good with these ideas so far. All right. Let's start applying some stuff. Okay. Down in the bottom right-hand corner of the sheet that I gave you today, there are 4 graphs. We are going to talk about those graphs today. You have room around them to make notes and try and mark them up as much as you want. You also have a little bit of space on the back side where you can, if you need to expand a little bit if you need to, or if you want to get a separate sheet, that's cool too, whatever works for you. All right? All right, so first graph looks like this. And I'm going to change distance to position, okay? And the first thing I want you guys to do for me is take 30 seconds and talk to the person next to you and describe for me the motion of this object represented by this graph. Discuss with the person next to you. Go.
And then it goes constant. What? Constant. What?
It's always constant with what it does, but it changes.
Motion
Constantly the same, constantly going up at the same, and then it constantly stays the same.
You're mixing some concepts.
Dude, I'm gonna do
Like what?
That's what I want you to figure out.
So what am I supposed to be doing? It starts out at going constantly, it accelerates, and then it. So what am I?
So wait.
Oh, it's not moving. It moves. It stops moving.
All right.
What's the point of that?
What?
What's the point of that?
Seems like a swim move.
Maybe it's red light, green light. Maybe it's a person playing red light, green light.
Oh,
And why'd you color with pink and green, not green and red?
Oh, because I wanted to use the highlighters that are a little easier instead of just blocking over the lines.
You can see through the red.
I could, but red like covers all
Try.
the lines. All right, so let's discuss. Like I said, if you heard it here, okay, a description of this could be a small child playing red light, green lights. Okay? So, what's true about the pink highlighted sections? The object is not moving. Okay? There's two ways that we can justify that or explain it. Okay? Steven, do you want to take one of them? How do you know that the object is not moving in those pink sections? There's no distance change, right? The distance or the position stays the same as the time is increasing. Okay? So that's one way we can explain it. What's the other way that we can explain it, right? Well, let's talk about the pink sections. We're still on the pink section. So we know that the object is not moving during the pink sections. Okay? One way we can explain it is to say, oh, the position is staying the same as the time keeps getting bigger. Right? What else could we use to describe an object not moving? Think about what we just talked about. How do we know there's no velocity? What was the previous slide we were just looking at? There's no slope. Actually, we should probably not say there's no slope. What is the slope of a horizontal line? Zero. All right? So, the pink sections, one, the object position remains the same, but the time goes on, or two, the slope is zero. Either one of those, you could say that means the object is at rest. Okay? So, what about the green section? There's a slope. What do you see about that slope? Is the slope increasing? The slope is remaining constant. So how would we describe the motion during that section? It's moving at the same velocity, right? There's a reason why I correct you, Maddie. I'm going to show you in a little bit, okay? So, if we look at position versus time graphs, right? Straight lines represent objects moving with a constant velocity. Horizontal lines are objects, so actually the pictures, or the little thing next to the graphs, just to the left of the graphs, there's some spaces for you to fill some stuff in there. Yep. Horizontal lines represent objects that are not moving or at rest. They have constant slope. It just so happens that constant slope happens to be what? Zero, because horizontal lines have zero slope. Good.
For like distance over time
Yep.
graph, could you ever have a vertical line? Because that would be no time.
Right. So that's a good question, right? A vertical line on this graph would mean the distance is increasing. A vertical line would mean that distance is increasing, but time isn't. Right? So it would be like, yeah. So it would be like, okay, here, and then here, right?
Does that make any sense?
No, it doesn't make any sense physically, right? Like, you could have a really steep slope, right?
Yeah.
But you can't have a vertical line because that means technically you were in two places at the same time. Does that make sense?
Yeah.
You have two y values for that x value, and you can't do that. So yeah, physically we can't do that. It could be a really steep slope, but it can't be vertical. Okay? Roddy, go ahead. Exactly. And from a mathematical standpoint, what do you know is the slope of a vertical line? Or what do we say about the slope? It's undefined. It doesn't have a slope. Okay. All right, good there? Picture number 2. There it is. Describe what's going on. Go.
Okay, so we want steady increase at the beginning, then red light, and then
It's red light, green light again.
Except there's more green lines
It's,
than red lines.
it's a pointer side. It's a continuation of red light, green light.
go as
There's some differences though.
Yeah, the kid's getting tired. He's slowing down.
He just disappears slowly.
accelerate, stop.
All right.
I have.
So, if we want a physical description of what's going on here, right?
A kid playing red light, green light, but then disappears.
Doesn't disappear.
Does his position be the same? Why is it nothing after?
If his position, wait, which section is his position the same? Green, pink, or blue?
No, I mean like after.
Oh well,
that part.
we just stopped measuring where he was. All right, so I mean, I suppose he could have just disappeared, but that just means we stopped measuring where he was. So okay, Ronnie, go ahead. Okay, so what's happening during the green section? That's green. So. Ready, go ahead. The object is moving with a constant velocity, okay? Then what happens from 1 hour to 2 hours? At rest, right? Then what happens from 2 hours to 4 hours? What? It's a really long red light, green light game. So blue is what?
Slower.
Okay, so from 2 hours to 4 hours, right? The object is moving again and moving with a constant velocity, but how does its velocity compare to 0 to 1 hours? The lower slope, right? This is not as steep, it's less shallow. So, green and blue are both moving with constant, or the object is moving with a constant velocity, but blue is slower than green, right? So, steep slopes are objects moving with a high speed. Shallow slopes are objects moving with a slower speed. All right, good there? These are written right next to the pictures too, by the way. All right, picture number 3. There it is. Discuss with the person next to you. Go.
Okay, so he's at red light and then he reverses. Okay, no. He stuck his car in the garage, right? He sits in the garage for a little bit and he backs down the driveway.
Maybe they're like backpedaling.
He was
They're
sitting on a bench.
backpedaling.
The guy walked up to him, Eddie, and he ran home.
But no, that's not, that's like some kids just really stupid. It's falling off.
Yeah, and then you just pass it out.
So he goes back, gets up, and he goes.
We jumped.
We definitely have a like good. Yeah. Can we say it?
We jumped from the. It rolled backwards. So it rolls backwards and it turn around.
All right. Let's just start with the description first, okay, before we get examples. All right, so what's happening during the pink section?
Constant. Or it's not constant, zero.
How would we describe its motion?
At rest.
It is constant position or at rest, right? Constant position means it's not going anywhere, okay? Now, what starts happening during the gray section? It's moving, but which way is it moving? That's the backwards, but negative would actually be a better description because, right? So, remember we said we're going to limit this right now to a line, right? Straight line, meaning we can either move forwards or we can move backwards, okay? But don't get confused, right, with, okay, let's say here, I call the corner of this desk the reference point. This is 0, okay? That means during this graph, I started here, 5 meters away from the reference point, at rest. Then I'm going to start moving this way. Okay? So What's different about that slope than the other slopes we've looked at?
It's negative.
It's a negative slope, right? Oh, yeah. Wrong button. Negative slope means that there are objects moving in the opposite direction.
Alright, can I get my
I want to get through the last couple pictures there.
No, I got one in my
All right. Are you ready? Next picture. Discuss with the person next to you. Go for it.
Okay, he's at rest, and then he goes up the hill, he goes back down.
Roller
He
coaster.
goes
This
back
guy
up
is
the hill.
contemplating whether he should go or not.
Roller coaster. It's just so easy.
And then he falls off the earth.
And then he just fall off there.
That is a terribly mean example.
This person has some internal turmoil with themselves, and they cannot decide if they should go somewhere or turn back. Yeah. This person needs to make up their mind if they're gonna go or if they're gonna not.
That last little hill,
So it's like,
oh my god. Yo, I started
person needs to decide what they're gonna do.
I'm starting zero.
That graph was my grade.
Oh. Okay.
How does it all turn out, Jafar? Turns out good.
I don't know. You
All right. So. All right.
overtime.
So before we just describe, and instead of just describing this motion, I'm going to give you a couple of possible test questions. All right? Might be a good idea to write them down. Never know, they might show up again here in a couple weeks.
Make a box.
What?
Put it in the box.
So,
What are we doing?
question number 1.
How many?
There's 2. These are both true-false questions. Now, I might not state them as true-false questions. I might turn them into multiple choice or something like that. But, okay. All right. So, question number 1: true or false? During the blue section and the green section, the object has the same velocity. The velocity of green and the velocity of blue are the same. True or false?
I can't tell because
Say again?
no numbers on mine.
Green and blue.
The answer is amazing because I can't tell.
They look parallel.
No. The velocity during the green section and the velocity during the blue section are the same. True or false? All right?
Are they the same length?
Average velocity.
There's not numbers on the side, so I can't tell if they're the same.
Okay, then it's false.
Do your best.
No, they're the same length based on this.
All right.
So I cannot give you an actual answer. I say maybe.
Correct answer. During the blue section and during the green section, the velocity or the objects have the same velocity. The answer is true.
See, I told you. What did you do?
Velocity depends on the slope, not where it is.
Yeah, but like this slope.
Green and blue, those green line and that green line and that blue line are parallel to the slope.
I told you.
I can't tell that.
By looking at
They may look parallel, but I can't tell that because I can't count.
Mr. Little would say, you don't know.
Let's say, you cannot tell unless it is marked.
You gotta
And I cannot tell the markings on that.
Order. Yes. Yes. Well, if they're parallel, what's true about their slopes? They don't have to be the same length because length would tell you how long did they travel at the same velocity, but as long as the slopes are the same, they were traveling at the same velocity. Okay? All right, are we ready? Okay, now, so sorry, go ahead. Yeah.
Oh, is there a difference between just like velocity and then average velocity? Yeah. Kind of. Yeah. Does that make a different velocity or like?
Not for this question, no. But there is a difference, and we can talk about that a little bit more later on. Okay.
For both of them, yes.
For both those, they have the same velocity. In that case, Jafar, the average velocity and the velocity during green and blue are exactly the same because straight lines, the average velocity and the velocity are the same because it never changes. Okay, we'll talk about that more maybe on Monday. Okay, tell me good.
You said it depends on the slope.
Yeah.
But they both have a different position, and
Position
delta,
doesn't depend
delta
on
x,
slope.
which is in rise over run, which is the slope.
Yep.
Displacement is changing position. So that's
But
a different
the
position.
times are different too.
Yeah, the times are different. So will they
Velocity is
just
a
end up equal?
ratio between position and time, change in position and time. The slope of this line and the slope of that line are the same. That means during that time, they were traveling the same speed. Oh, sorry, they had the same velocity. Okay?
Yeah, that makes sense.
All right, so question number 2. True or false? Question number 2. Green versus orange. Green versus orange. The object has the same speed during green as it does during orange.
Speed or velocity?
I mean speed. So, the object has the same speed in green as it does during orange. True or false? You can discuss with the person next to you.
No. No, because it'd be a right angle.
Guys, it's false. Yeah. Because speed has changed position. Speed has changed position. It doesn't? Wait, what? It does? It doesn't? Okay, then it's true. It's true. No, we gotta prove it's perpendicular. So let's make sure the same. No, unless if we're in our compass out, we gotta make sure they're opposite reciprocal. If they are,
How do you tell based on this graph?
One looks great.
can I use my compass to make sure it's perpendicular?
The green line's curved.
Dude, we gotta see opposite reciprocals here and make sure it's perpendicular.
It needs to be perpendicular slope. No. No, it doesn't. No, it just has to be the
Oh, no,
opposite.
that's velocity.
I was right. I was right.
So they are.
Wait,
No, but it's not touching the angle.
I just want you guys to know. Nobody in another class brought that up, like even.
The right angle.
Just
That doesn't
not even bring that up. So the answer to that question is the speed during green and orange is the same. So the answer is true. They have the same speed. So
How can you tell?
what is that blue? Yeah,
I'm not in the opposite
I'm not
direction.
trying to short on that. All right, I want you to understand why they have the same speed.
How can you tell? I understand that it's the same speed just in the opposite direction. I don't
I know.
understand how
You can't have, well, if it's the same speed but in the opposite direction, well, let me. All right, so
it has to be the same
So-
angle. What I do this
the answer to the question, green and orange have the same speed is true. Because speed is a scalar quantity. it only tells you what? Magnitude, or in this case, how fast, okay, which is how much in this case, right? It tells you how fast, but it doesn't tell you what? What direction, alright? During green, it's moving forward at a certain speed. During orange, it's moving backwards, but it's moving just as fast backwards as it was forwards, right? And the blue square on there, right, is because of the fact that two lines that have the same absolute value of slope but different signs are perpendicular to one another. So if they fit in the corner of the square, that means they're perpendicular to one another.
A 90-degree angle.
Speed doesn't tell you anything about direction. The absolute value of those two slopes is exactly the same. One's positive, but one's negative.
It's not always going to be perpendicular.
Because, well, one, you can look at it, but two, if you know geometry, right, you know, two lines that are perpendicular to each other have the same absolute value of slope. One's positive.
Why? If something's it's going slow and it's going slow.
Alright, so
If something like this, it's going slow this way and slow that way. These two lines are not perpendicular.
then they wouldn't be the same speed.
Why not?
I always say that I want this to go like, no, you can't.
No, because distance again doesn't tell you which direction you're going. Here, from here to here is the same distance up on the y-axis as from here to here is down on the y-axis, but when you're talking about distance, it doesn't matter which direction you're going.
You said orange.
All right, so, Dylan, go ahead.
If
No.
we're doing one-dimensional thing, wouldn't it be someone going and then going back?
Yep.
And then going forward again?
Yep. But the whole time, now, Devlin, this is kind of unrealistic because they're going forward at a certain speed, backward at a certain speed, and then forward. Those are the same speed the whole time. But in real life, you can't just go from going forward a certain speed to automatically going backwards at that same
Well, I
speed.
mean, if you run backwards, stop.
You have to stop. And that's where this graph comes in, but we'll talk about that on Monday. Okay?
It will not always be perpendicular because